So as was mentioned, my name is Veronika Zelinková, and today I will be here talking about Metal, and specifically about Metal with SwiftUI. So as iOS developers, we like to make things looking beautiful. The animation always have to be sleek, everything is user-friendly, the code is sexy, and then we hear the word Metal over here, and we turn away. Like, we don't want to hear about it, we don't want to learn it, we don't want to work with Metal. Actually, I don't know the exact numbers, but I know I used to work in an agency, and I remember about like 5 of my 40 iOS colleagues ever touched Metal, which means they ever like built it, any Metal code. And I know I can't generalize this for the entire iOS population, but I wouldn't say the numbers will be any different. And it's such a shame, because Metal lets us create things which are very extraordinary, very new and creative, and actually also extremely fast and efficient. And this might be a little bit subjective to me, but also Metal is tons of fun. And if you already ran your half marathon in your 30s and you are looking for some new adventure, I think learning Metal could take you a few years. So just to sum it up, this is the last meme of the presentation, don't worry. And just with the talk, I will tell you something about Metal, how to use it, what it is. I will try to motivate you, inspire you. Just, I hope that after you leave this presentation, you will know what it is and that you will know where to use it and how cool it is. Don't be scared if anything looks too, not difficult, but scary, because it can look scary. Sometimes I will provide you with all the code after, so you can like check it out. So what is this Metal which I'm talking about? Well, it's not a music genre, it's something way much cooler. It's actually a low-level GPU programming framework from Apple, which got introduced 10 years ago on the dub, same as Swift. And it's mostly used for gaming, video processing, any scientific computing, machine learning, basically anywhere you need the direct access to the GPU, or you work with tons of data and you need to make the work fast. Previously, Apple actually used OpenGL, which they got rid of in 2014 when they introduced the Metal. And why did they do this? Well, back in 2014, OpenGL actually sucked quite a lot. And it had many issues which got solved with Metal. First of all, OpenGL was designed to work on an architecture with like separate CPU and GPU. So to pass the data from CPU to GPU, you would have to copy the whole input, the whole memory. And with Metal, as it works on the Apple chips, where the CPU and GPU are on the same chip, you can actually just pass the access from CPU to the GPU, just share like the memory, and it will make it more efficient. That's not the only reason. There are like very many more. Like the second will be, for example, the shaders previously in OpenGL were built during the runtime, and with Metal we could build them in compile time, and all of this made Apple so cool, so fast, and actually a great base for all of the frameworks, and which we are currently using nowadays. Metal is the reason why they work so nicely. So if you ever used like UIKit, SwiftUI, SceneKit, you probably did. You already worked with Metal underneath. So when Metal is this cool, why no one actually wants to use it? Well, to write a simple triangle in a Metal, you are looking at 100 lines of code. I actually wrote it, so I know, and I counted it. And everything can go wrong during this time. Like you specify the pixel format differently, or you can't really debug it, and nothing will be drawn out. To set up a simple rendering pipeline, and the image is not loading here. You are looking at you have to set up the vertex shader, fragment shader, you have to define your pipeline state, you have to add the pipeline state to your, like, let's say, a render command encoder to draw the rectangle, you have to put it into command buffer, then you send it through a queue to the GPU, to the metal device, and then you rendered one rectangle to the screen, and which is terrible. But luckily, from iOS 17, Apple introduced us with these SwiftUI view modifiers, which make this all easier. They are called the color effect, distortion effect, layer effect. Each of them does something a little bit different, and this is what we are gonna talk about today. So here I'm still talking about shaders, and you can also see it as a parameter in the SwiftUI view modifiers. So what it is, shaders are tiny functions that run on the GPU in parallel. Like for the scope of this talk, let's imagine it, we have a texture of 10,000 pixels, and we write one small function that will return a random color for a specified location, or just returns a random color. And this function will be run for every pixel at the same time. So if we would write this on the CPU, we would probably write to 4 conditions, and it would color the pixels one by one. But on GPU, it's a little bit different. We write one function, and it's run at the same time for every pixel on the screen. So it's like a mental shift in the way how we are coding stuff on the GPU than compared to the CPU. And we check the code on the GPU. When we define our function, to use the SwiftUI modifiers, we have to always start with the stitchable attribute, which lets us use the function in the SwiftUI context. Then we specify the return value, which is half whole, a color in this case, name of the function. Then each SwiftUI view modifier effect lets us or gives us some required parameters, which we always have to have here, otherwise it wouldn't work. And also some custom arguments, which we can pass from CPU by ourselves, which are usually a color, image, or some vector, which is like a position, frame, or any size. And then on the CPU, we just call this color effect on some SwiftUI view. And in this case, we are calling the color effect. And we can actually very easily to access this function written on GPU in the .metal file through the shader library, which is given to us already by Apple. And if the name of the function and the arguments match specifically, first of all, the view modifier, so we have the required parameters and some custom ones, and then here we added the custom parameters, so it's the color, image, and some position, which is a touch position. So if it matches the function signature, it will automatically run the function for us. Let's just, I know I talked about some half-word float too. What does it mean? Well, it's the metal shading language. It's the language that we write shaders in. It's also from Apple. And basically, it's kind of understandable by itself, at least for the scope of this talk. Floats and float tools we will probably use for some positions. Half-word is like a vector of 4 elements, which we will use for colors. And then we can, it actually gives us many predefined functions, which we can use, like maxing, flooring, the length, square, stuff like that. And also we can perform many math operations on the vectors and just get the length of the vector or normalize it. Yeah, beautiful. So let's start finally with the view modifiers. The first one is the color effect. And it actually works very simply. So what we get on the input every time, we get the position as a float to, just a size, where the pixel is located in the texture, and then we get the color of the current pixel. So here we would get that the pixel is located in the middle as the position, and the color is light purple. And we are supposed to return half-4, which is also a color. So we will just return what color should be on this pixel. And then we can also specify some arguments which we want from the CPU. This is the SwiftUI shader. And let's see it on an example, actually. We will just try this very simple example. We have this Cocoa Heads logo with a transparent background. And what we would like to do is to recolor it to a color which got specified on the CPU. So in this case, it's the purple color. Just to show you around how we work with the colors, it's stored as half-4, as vectors of 4 colors with red, green, blue, and alpha is the fourth one. So 1 is the most prominent color, 0 is the less dominant color. So for red, it would be 1, 0, 0 for the green, blue, and 1 again for the alpha. So with this knowledge, we can already very easily implement this recoloring shader. And what we want to do is, as I mentioned, we want to recolor the non-transparent pixels. We are getting the position and the current color, which is like given to us. We always have to define these parameters. It's like how the color effect works. And then we define one new argument, which is the new color, which is the argument that we are passing from the CPU, and the purple color that we want to recolor it to. So actually, we can just easily check the pixels at the current location, and if the pixel is if the pixel's alpha value is close to 0, it means that probably this pixel is transparent. So we'll just return again the current color. We will keep it transparent. But if actually the alpha value is bigger, which means like in this case, the alpha value, probably like there is some other color, we will just return the new color. And we'll very easily recolor the shader. If we, let me show it in the code. So here we have this image with the logo, and currently it's recolored to purple. If I would comment it out, you can see that it turns to white, back to white. We can also recolor it to any new color, like a yellow in this case. And if the head signature of the function wouldn't match, we can do it by, for example, adding one more parameter. You can see that the function just will be skipped. It won't work because the signature of the function is not matching the defined requirements on the GPU. So it was quite easy. Let's try something more complicated, because the second thing which we can do with the color effect is we can add filters to the textures, any like effects, filters. And for this example, I just picked the single like grayscale effect, but I believe you can come up with many more. And I will show you how easy it is to actually make an image grayscale on the GPU. So just like some color knowledge, basically if the red, green, and blue colors are the same, it means that the final color will be, the final mixture will be in a shade of gray. And with this knowledge, we can already implement the black and white shader. Here you can see we are not passing any custom argument. We are just using the default ones. And what we can do is check for the luminance by averaging the red, green, and blue values, and just return it as a new color. And it would make the shader black and white. If you would play around with the luminance, it would make the grayscale either more like lighter or darker. That's totally up to us. We could make any more effects we would like, but this is just a single grayscale. So the third thing we can actually do with color effect is like any custom drawing you can imagine. So we don't have to really apply the effect. We don't have to really apply the shader function on any texture. We can also like create something on our own. And here what you are actually seeing, it's not a SwiftUI animation, but this is a visualized 3D mathematical function. If we check it in the code, it works the way that there is one big dot in the center, and then we are going by touch around. If you get closer to the dot in the center, the dots gradually blends in together, and we get out the dots split. Here we can see we are using two custom parameters. The first one is the drag gesture, drag location, which we are getting from the drag gesture and passing it in as a vector of two values. And also we are getting the frame size from the visual effect, which is really cool. If you will be working with shader, just use the visual effect to get the size, because we will need it for normalization. So as I mentioned, we get the touch and the frame size. And this is what we will try to visualize, actually. It's way easier to explain it on an image. This is a 3D function, And you can kind of see that we are already getting the plane in the middle, which kind of looks like what we are trying to visualize. And you can see the big circle in the middle and the smaller single on the circle on the side. And they are gradually blending in. And then if we check like the z-axis value, it's around like z-axis at 1, and we can make it like 2D. This will be actually the function that we will just like drawing out or visualizing. So we will check what's the value at 1, and if it's gonna be less than 1, we will color it purple, and if it's gonna be above 1, we will color it black. So usually, like when we write shaders, there are some functions that we defined, and we are just visualizing them. I mentioned we need the frame size for normalization. That's because we are getting even the default arguments, even the touch position, everything is in the user coordinates, so we have to normalize it to create the function. So we will just start by creating the dot in the circle, the purple dot in the circle, which is like the bigger one. So that's why we need the screen center. We can get it by dividing the frame size. And then we get the position, the direction of our current pixel to the screen center. And if we get the length, it will give us values which are under 1 in the center, and then other ones which are like outside. It will basically, if we draw the C distance out, it will give us like the gradually blended circle in the middle. And we are multiplying it by 10 just to make it smaller and visible. So now we just need the touch position, the smaller dot, and we are creating it at the touch position. So we are using the position to the center, which we already defined, and the same way we are just subtracting the vector of the current pixel position to the direction of the current pixel position to the center to kind of move the touch to its correct location. And we are just multiplying it by 20 to make it even smaller. So if we would draw the t distance out for the values where it's smaller than 1, it would give us purple, and the ones which are bigger than 1, it would give us black. And to blend the dots together, we can just use any like function. We can usually like multiply it. Here I'm just like squaring the c distance and then multiplying it by t distance, which gives us this particular function. But if you wanted to make it a little bit differently, you could write your own like multiplying function. So if we put this all together, and as I mentioned again, now we got this beautiful function, so we will check where the function is like less than 0, and we will draw purple. And for the ones when it will be more than less than 1, we will draw purple, and where it will be more than 1, we will draw black. So just a simple if condition, and this is how we are getting the dots shader, which is like interactive mathematical function visualized. Okay, so not only this, we can, for example, write any textures. There was a guy yesterday who was showing me that he actually writes a texture for his app in Metal. But I will just show you maybe the code for this quickly, because we will not write it out, because it will look kind of like this, and I don't think you really want to get into it. Or I was playing around with drawing any like custom loading indicators. I'm not sure how you would write these in SwiftUI, but it's actually quite simple to write them in Metal. And there are many, many more things which you can easily write. So the second effect is called the distortion effect, and it works very, very differently, and lets us do extremely different things. The main difference is we are not getting any color here. We are getting, this image missing again. We are getting in the position of the current pixel, and we are just returning a different position. So we are actually returning a position where the new pixel should be sampled from. So now here we can't introduce in any like new colors, but what it is really cool to use it for are any like distortions, any transitions. I saw examples where people were using this to make like transitions between view controllers, between pages, just with metal, and you can basically create any transition you want, and it's also like highly efficient. So we are introducing here in the SwiftUI new parameter, which is called the max sample offset. And it kind of, I will visualize it on an image. It kind of lets us define how much the offset can be, how much we can sample apart. Basically, if the max sample offset is 0, the image will stay in the bounding rect of the texture. But if we also animate it with time, as we are animating like the moving, the image will be moving outside the frame. So it's a really, really nice parameter. What we'll be doing with the distortion shader, I will try to show you how to very easily do pixelation. Here we are just animating pixelation over time. And what we can use for this, I'm just showing you, we can use the timeline view with the animation parameter, which gives us the elapsed time, which we are then passing inside to the pixelate shader. And based on the elapsed time, we are like slowly animating the distortion. But if you want to make any like time animation in the future inside SwiftUI, I recommend using the timeline view. So how does pixelation actually works? Well, a texture is made of many, many pixels, and pixelation is basically just like grouping the pixels into some groups, and basically adding one single color for this like group of pixels. Here we are just like sampling. We will like return a new color of the pixel for every group, which is on the top left. And it will end up like this, basically. So then it will make the image pixelated. Just to start it out, as you can see, we are not getting any color here. And we are also returning the float 2, not half 4 at this time. And we are getting the strength of the pixelation as the time, which we pass from CPU. And actually, the distortion can be done very easily, because here we have some position of the current pixel, and we are like dividing by strength, but then like multiplying it again by strength. So we should kind of get to the same point. But as we are flooring it, it kind of moves the pixel during dividing it to the groups. So we will always get the top left pixel of the specified group based on the strength. And then we just can very easily return the XY as a new location. So it will sample the pixel from this new location and return it like instead for the current position. And so I got the pixelate shader. Okay, the last but not least is the layer effect. And actually, as you probably imagined, the color effect had, and both the distortion effect had some issues. First is that the color effect can't access its surroundings. It lets us draw extremely nice things, but it kind of doesn't know like what's around it. But then the distortion effect can't return a custom color. It was always returning a position. So layer effect kind of fixes both of this, but it's less efficient, so don't use it where it's not needed, by giving us a layer. So now here, as a default argument, we get a layer, which we have to include. And the layer is very simple struct. It just holds the 2D texture, and it gives us this sample method, which we can just call on the layer with any position, and we can basically, like in the current pixel, we can check like what's around it, like what's on some like other coordinate in the texture, and make our decision of the color based on that. It also uses the max sample offset as the distortion effect did. And what I will try to show you here is this wave shader, which kind of creates this waving animation at the place where you touch the screen. And then, just to not make it just a distortion, we will add a color to the wave effect to kind of also color the distortion. will maybe show it out in Xcode also. So here we are kind of, where I touch, it will make the yellow wave. We have some parameters that we are getting, passing in. The first one is the width, which kind of adds like how much the wave should be. So if we would make the width of the donut bigger, it will do a little different distortion. By the amount, we can handle how like the strength of the distortion. And the tint parameter lets us also change the color. So if I change it to pink, it will be pink. And also we are passing here the elapsed time in, which we use to kind of gradually move the wave like over time. It's like the spread, like how big the circle should be. So the first thing we need to do is create the distortion. And we have to kind of somehow distort the texture, and then we will be trying to like map the distortion to only the donut. We can do this by very easily, again, like checking the direction to the center from the current pixel's position. And if we draw this out and we normalize it, time by the spread, like how much should be distorted at this moment, which is the time. And we normalize it and we get the displacement subtracted from the current pixel position, and we sample it out, we really get this beautiful distortion if we draw it out. To add the touch gesture, it's not that hard actually, we just remove the center and replace it with touch. So now we added the touch parameter, so the distortion is happening from the point where you touch the screen. And now we want to limit the distortion. So here we are limiting it only from the outside, so you can see like in the middle it's still distorted, but on the outside it's not anymore. And we can do it by using the smooth step function, which is a very popular function in graphic rendering, and it lets us handle smooth transitions. Basically it has three parameters. The first one is the first edge, second edge, and some value which are passing inside. And if the value is like less than the edge one, it will return 0. If it's bigger than edge, the second edge, it will return 1, and it will smooth out the middle based on some Hermite interpolation. So here we will just create this map from the direction to touch, and we will create the bounds by it should be like from the spread to the spread minus width. So based on this, we will create like the outer distortion. If we like sample it out and draw it, it will draw this like outer map. And maybe we need to also, this is in the code, and to also create the inner distortion. We can do kind of the same. We will just create the inner map, create the donut by getting the edges as spread minus 2 times width and also spread minus width, because we are getting the map from the inner side. And if we multiply the maps together, we get this a donut shape. And now it's very, we can like put it all together by creating this wave shader, by just drawing out the displacement in the position where the map is. And to add the tint, we will just pass in the tint color, and we will just multiply the tint, like add the tint to places where the map is, and just add it to the return color. So just to summarize it, Apple introduced us with these beautiful 3-view modifiers, which are available from iOS 17. We can use the color effect to do any like custom drawings or any filters, effects on images. Then we have the distortion effect. We can use to any like distortions, transitions. Usually when we want to like only move the pixel, but we don't have to specify a new color. And then we have the layer effect, which is less efficient, but lets us do like everything together. and kind of we can do everything with the layer effect. It has some limitations. The first one is that it can be used only for SwiftUI views. So it means that if your SwiftUI view is actually a UIKit view underneath, the code will show you a placeholder warning image and some message, and won't work at all. The second one is the one parameter. When we are passing in the custom parameters, we can also only pass like one additional image texture. And the third one, which I found out mostly when I was drawing out the pink texture, when you create some very, very advanced shaders, the performance was kind of lagging. Like I didn't experience it with any like easy shaders, but if you try to do anything like huge, like people usually create like clouds or nature, SwiftUI is not handling that very well. And the fourth limitation would be, you know, with Metal, you want the access to the GPU, you have like control over everything. And here, as you could see, we don't have that much control. Like it comes of the advantage of like no setup, it's very easy to use. But at the same time, like we can't really specify much if we are specifying fixing the pixel format, like completely like everything. But we don't have that much control, which we would probably want to have. So where would I use what? Well, if you are doing gaming, I would tell you go back to the manual setup with UIKit, or if you are doing live streaming or drawing like camera textures or doing very, very heavy filtering effects like graphics apps, you will still have to set up the Metal manually. But I think actually there's a place for the SwiftUI modifiers in case you want to add any like small texture to your app, you want to do a custom transition between your SwiftUI screens, and all these small things are currently possible to do with these really, really nice view modifiers. I showed you some examples, but what you can actually normally do, you go to some shader library as like shader toy, and you get the shaders which are written in OpenGL like language. And you kind of make them use for your own vein. So all these things which I was showing you out, and even more which you can think of, probably someone coded like before. So you don't have to think about this all like yourself. You probably can use some from some libraries which are already out there. I'm mentioning the Inferno, which is a library specifically with like metal shaders. There are some like really nice transitions which you can use. And when you would want to learn something about Metal, there are not that many resources, but you can also go to Metal by Tutorials, which is a book by Codeco, Metal Programming Guide, and the Apple documentation actually has quite good examples. There is the source code and presentation for everything. And thank you so much for your time.